Hello, welcome back to Larry's Classroom. Today we're going to talk about our first electrical component, which is resistors. The two main characteristics of resistors are the resistance and the wattage. The wattage is the heat dissipation rating of the resistor. Resistors come in a wide range of values, from low values up to what they call K ohms. And if we had 1 K ohm, is equal to 1,000 ohms. So the kilo, is a prefix that means times 1,000. If we have 2 megohms, and we use an M, megohms, that's equal to 2 million ohms. So you'll hear people talk about 1 K ohm, 1,000 ohms, 4.7 K ohms, 47 megohms, etc. But basically kilo, the prefix kilo means times 1,000. Mega, the prefix mega means times 1,000,000. Now, the most common type of resistor that we see is a carbon composite resistor. And this is a little bit oversized, and there'll be stripes on it that represent the value of the resistor. These carbon composite resistors come in wattages from 1/4 watt up to about 5 watts. And that, like I said before, is how much heat can be safely dissipated from that resistor without overheating it and destroying it. We have wire wound resistors. Kind of hard for me to draw a wire wound resistor, but I'll attempt to. It's usually kind of a circular thing with a couple tabs on the end, and you can kind of typically see the texture of the wire wrapping around this insulating core, and it's usually got a insulating ceramic or paint or something over it. And the wire wound resistors tend to be lower values in resistance, but capable of dissipating greater amounts of heat. And they might come in sizes from 5 watts to 100 watts or more. Now, when you talk about resistors, we first start thinking about the resistor color code, and I put that up here. And we have colored stripes that show up on the resistor, usually painted on there. Black is 0, brown is 1, red is 2, orange is 3, yellow is 4, green is 5, blue is 6, violet is 7, gray is 8, white is 9. And I got a picture of I've drawn of a resistor here. And basically the first 3 stripes typically tell you the resistance value. If I had here a brown and here a black, and here a red, now how would we read those colors to understand the value of this resistor? Well, if we look at the chart, I want to change this around. I want this to be black and brown, not brown and black. Yeah, brown. I guess I had this the way I wanted it. And black. So we see that brown is a 1. So the first digit in the value is a 1. We see that black is a 0, so the second digit of the resistor value will be a 0. And now we see that red is a 2. That basically means times 10 to the second. And we talked earlier, and we realized that 10 to the second is equal to 100. So this is basically 10 times 100, which is 1,000 ohms. So if it says brown, black, red, that would be a 1,000 ohm resistor. And another way to look at this, rather than going through all this 10 to the second stuff, is just say, again, we'll say the brown is a 1, the black is a 0, and the red is a 2, so we just add 2 zeros. So we get to our 1,000 ohms that way too, without thinking about the powers of 10 situation. Now if we have this 1,000 ohm resistor that we're talking about, and we have no third band, that means the standard notation is that is a 20% resistor, which that means that this will be 1,000 ohms plus or minus 20%. Well, 20% of 1,000 is 200 ohms, so this could be from 800 ohms to 1,200 ohms and still be in proper tolerance. If you had a resistor with brown, black, red, and no other stripes, and you took your ohm meter and you measured it, and you measured anything between 800 and 1,200 ohms, that resistor would be in tolerance. And 20% resistor is a little less expensive to make than ones with greater precision, and not every circuit requires that kind of precision. But we're going to talk a little bit about tolerance anyway. Same 1,000 ohm resistor. If we have a gold stripe for the third stripe, or fourth stripe, gold, that means it's a 5% resistor. You see you've got tolerance, gold 5%, silver 10%. Well, 5% of 1,000 ohms is equal to 50 ohms. So if we had brown, black, red to indicate a 1,000 ohm resistor, and we had a gold stripe indicating its 5% tolerance, this could be 1,000 ohms plus or minus 50 ohms, so it could be 950 ohms to 1,050 ohms and still be within tolerance. If you had the gold stripe and you found it to be 850 ohms, this would not be fulfilling its expected tolerance. So it would be out of specification. And we'll look again at if it was a silver stripe. That's an indication of 10%. So 10% of 1,000 ohms, that means that we can be within 10% of that. So this could be 900 ohms to 1,100 ohms, or 1,100 ohms, and still be a proper in-specification resistor. And we've talked about multipliers when they fit the black, brown, red, these colors. You can have them, gold can be in the fourth band as a tolerance rating, or it can be in the multiplier third band as a multiplier. So if this was gold, that would be a multiplier of 1/10. So we took this same resistor, we had a brown, that's the 1, and the black, which is a 0, and we multiply this to times 1/10 times 1 over 10, that becomes 1.0. So we could look at that 1/10 as moving as basically 10 to the minus 1. That equals 10 times 0.1, 1/10. That would be moving this decimal place 1 to the left to reduce the value, giving us a 1 ohm resistor. With the same color, except for now this is silver. Silver is a 100th. So if we took the 1.0 and we said we're going to multiply this, silver would be like 10 to the minus second, which would be 10 times 0.01. Well, then we would take that 1 and the 0 and we move the decimal place 2 places. Of course, we've got to add a 0 to move it here. So that gives us, no, we don't have to add a 0 here. No, we don't have to add a 0 to move it here. We don't have to add the 0. We needed, so 1, 2, that gives us a 0.1 ohm resistor. So for the smaller values, which you don't see that often, you'll be seeing these gold and silver multipliers. Usually in the values that you typically see, we have the whole numbered multipliers, and we use the same colors for the first 2 digits for the multiplier, either way. Now you notice that I've got first digit, second digit, multiplier, and tolerance. You'll see this done. You can tell which way to go reading this because the bands will be towards one end of the resistor and the one closest to the end is the first digit. Or you may see a greater gap, which tells you that that is separating the tolerance band from the value bands. Let's say that we have these values. We'll do a couple more. The first value is red. The first stripe, red. The second stripe is a green. And the third stripe is a silver. And we're not going to concern ourselves with the tolerances. And we did say that tolerance 5% gold, silver 10%, no tolerance band 20%. So I'm going to write that over here, no tolerance, just so we don't forget. This band is a 20% resistor tolerance reading. Say we have the red, green, silver. We'll look at the red, that's 2. The green, that's 5. So we got 2, 5 for our 2 digits. Silver is a multiplier of 100, 10 to the minus 2, so we move the decimal place 2 this way. So this equals 0.25 ohms, or it could be said 1/4 of an ohm. Now, we talked a little bit about wire-wound resistors, and wire-wound resistors are usually lower values and greater power dissipation. And occasionally on small wire-wound resistors, we'll see this color code on here, but very often the wire-wound resistor is large enough that they actually print the value on it, so you can just read it off of there. Now I'm going to erase this here resistor color code chart. And we're going to talk a little bit about variable resistors. Variable resistors they're made as wire wound. They're also made as carbon resistors, and they're designed. I'm going to show you the schematic. The schematic of a schematic representation of just a fixed resistor is usually just a zigzaggy line. We're going to draw a typical schematic demonstration of a variable resistor, and you'll often see a little arrow which kind of indicates you can pick off more or less of that resistance as you adjust this. And these can be what you call linear taper. So if you move it a fourth of the way, we're going to draw a picture of one, and the shaft coming out of it. And they can typically be turned slightly less than 360 degrees. So if you turn this thing all the way down, you end up putting your wiper way down here. I'm going to mark these A, B, and C. A, B, and C. So you're basically, when you turn it all the way down, you basically have zero resistance from A to B, and the full value of whatever this particular variable resistor is from B to C. If we go to a fourth of the way, we'll go about a fourth of the way here, we would have, say this was a 10, let's call this a 10K variable resistor. At a fourth of the way, we would have about 2,500 ohms from A to B and about 75 ohms from B to C. And 10K ohm is equal to 10,000 ohms. Again, the K kilo to indicate times 1,000. 50%. Then we have the same amount from A to B, so we end up with about 5,000 ohms here and 5,000 ohms here, and always you have the full value of the variable resistor from A to C, as you can kind of see in the schematic representation. 75% position. You don't usually see drawing this wiper, this arrow, in different places on the schematic diagram. It's generally the center, but I'm doing that to kind of illustrate my point. When we go up here to 75% position, we have 7,500 ohms from A to B and 2,500 ohms from B to C. If we were to take this all the way to clockwise up to the top of this thing here, then we end up with 0 ohms from A to B and 10,000 ohms. I got that backwards, excuse me. We end up with 0 ohms or 10,000 ohms from A to B and 0 ohms from B to C. And you kind of see that we're picking off more or less of the resistor. Now, what I've described to you is what's called a linear taper pot, linear taper variable resistor. And basically, if I move to 25%, the resistance changed 25%. We also have resistors with different taper. An example is what we call audio taper. And what happens on the audio taper is change at the bottom represents a far lesser change in resistance. Maybe we go from 0 to 25% on the wiper, but maybe we go from to only 5% here. Maybe we have 5,000 ohms or 550 ohms, and the remaining 9,950 ohms here. And what happens with the audio taper, as you move it further and further from minimum to maximum, the resistance changes more for each degree of movement on the shaft. This allows you to make careful precision adjustments at low levels and still be able to get the full desired range at the upper levels. And this, to some extent, mimics the way your ears work. Your ears can tell, at low volumes, can tell smaller differences in sound than at large volumes. Now we're going to, both the rheostat and a potentiometer are both a variable resistor. Why do we have two terms? The two terms are more related to how they're used than to whether they're a variable resistor or not. So let's talk about what we typically see a rheostat doing. We're going to draw us a battery. I'm going to draw this the pictorial type. Here's a battery. And we're going to go up here through an amp meter. And we're going to go through a load, which might be, I'm just going to say it's a heater. And I'm going to draw kind of a pictorial representation of a rheostat. We got the wiper moving here, and these are our terminals A, B, and C, just like we had on our variable resistor diagram a little bit ago. Basically, what we're doing here, we're not using A. We're just picking off part of the resistance between B and C in order to change the current through this heater and consequently change how much heating it does. So in a rheostat situation, we are varying the resistance. Now we're going to talk a little bit about potentiometer. Rheostat. So here we got a rheostat circuit. Now we're going to do a potentiometer circuit. And typical use of potentiometer, though it's still a variable resistor, is slightly different. Let's say that we've got 50 volts supply here from, we'll just say from a battery. And we'll do this schematically this time. We've got a variable resistor which we're using as a potentiometer. And this would normally be a linear taper. Well, it could be either, but we'll assume it's linear taper from this point. 50 volts, so from here to here we have 50 volts. But from this point to this point, our voltage is going to vary depending on where we set the pot. If we set this for 50% positions, we got just as much resistance from A to B as we got from A to C, or B to C. We're going to end up with half the voltage here. Half the resistance, half the voltage. We end up with 25 volts. And if we have this set down at 25%, and like I said before, we don't see this move, but 25% would get us to about 12.5 volts. So we could use this potentiometer thing, we usually use it to pick off part of an electrical signal, the desired amount we want. At 75% position, we'll see 37.5 volts. At 100% position, we move the wiper all the way up to the top, so we're reading the voltage across the entire variable resistor. We'll see the full 50 volts. And you can also, if you look at that, when we have our voltmeter from this point to that point, we're basically connecting it to one side of the battery, and we're connected through this wire to the other side of the battery, so we get the entire battery voltage. Now, we might, in some case, use a potentiometer as a rheostat. And an example, we can't, potentiometers aren't designed to handle high current like rheostats, which are typically wire wound, like we needed for controlling this heater. But maybe we have a tone control and an amplifier, which is a combination of a capacitor and a resistor, and we want to vary the tone from high to low by adjusting the resistance of this little network. Now, there's not a lot of current through this tone control, so we don't need this big heavy-duty wire wound resistor, but we're still using it like a variable resistor instead of like a voltage divider. Here in the potentiometer case, we're using the physical variable resistor to pick off more or less of a signal, maybe setting the bias on an amplifier, maybe picking off how much volume you're taking from one stage of a radio receiver to the next. Where in the tone control situation, we are actually varying the resistance to vary the tone response of the tone control. So that would be a case of using a this is a potentiometer circuit. I want to write that down here. Potentiometer. Potentiometer circuit. And this is that's rheostat circuit, potentiometer circuit. And the basic difference here is we're using the variation of resistance. Here we're using the variable resistor to pick off part of a signal. In the tone control circuit, you might have a capacitor and a situation like that where you're adjusting the just the resistance from this point to this point to change the time constant of this R resistance and C capacitance circuit. So that would be the case. We're using a potentiometer as a rheostat because we're interested in the resistance. So the difference between the technical definition of rheostat, you're interested in resistance. Potentiometer, we're interested in tapping off part of a signal. So this is basically a potentiometer as a rheostat. Circuit. So we typically think of the wire wound ones as potentiometer or as rheostats, and the carbon ones as potentiometers. And the reason we typically need much more heat dissipation capability here than we do in this kind of thing. Now here we are interested in the resistance thing, but we don't need the heat dissipation capability, so we can use a potentiometer as a rheostat when we're just varying this time constant of this little circuit, which we'll learn much more about time constants in the future, but just kind of a quick mention of what that circuit, what that's about there. We talked a little bit about the power rating resistor. And the power rating is basically how much heat can be dissipated. And we mentioned that small carbon resistors are rated typically from 1/4 watt to about 5 watts. And a wire wound resistor might be 2 watts up to 100 watts or more. And this is wide range of resistances, where the wire wound is usually lower value, 50 ohms or less, maybe. Now, where might we use a wire wound resistor? I'm going to draw this thing and I'm going to say this is a variable speed DC drive. And now what does that do? It basically, in the simplest term, puts on a variable voltage to change the speed of a DC motor. If we have this, say this is a 3600 RPM motor that we got on it. Now let's say it's a 1800 RPM DC motor. And we'll say it's a 200 volt. If we want to run that thing at 900 RPM, we're going to want to put about 100 volts to it, and that's what the variable speed, I'm just going to put an M for motor, DC drive is, in its simplest terms, a variable voltage supply for that motor. If we're motoring along, we're running along nice and happy at, say, 900 RPM, and we shift it down to 100 RPM, which would be, well, we'll go to 180 RPMs. So that would be down to roughly the 20 volt range. Initially, that motor is going to want to push power back into that drive. If that happens too long, we end up with extra power, and we have what are called dynamic braking resistors. And this is a way to get rid of that extra stored energy in that rotating motor. The dynamic braking resistors, depending on the size of it, can get quite hot. So we usually use wire wound. Resistors, and they can go up to several hundred degrees, maybe as much as to where they almost get red in color, 400 or 500 degrees, where a carbon resistor is good for maybe 185 degrees Fahrenheit. Or this might be good for 400 degrees Fahrenheit. And either way, you burn your fingers on them, but you can see that because of the amount of power being bled off in this, we need this wire wound resistor so it can absorb significant amount, and it has to be able to handle the temperature from that. So if you run these things too hot, if you run this too hot, it'll probably burn open. You run this guy at, say, 212 Fahrenheit, it's not going to last long. It might burn open or change value. So there's a rating at which these resistors can survive, but the wire wound one can survive a significantly higher temperature than the carbon resistor. Now, we're going to talk about how resistors combine in series and parallel. All my resistors that I'm going to use in this example are going to be 20 ohm, I'm going to say 10 watt. 10 watt. If we put two of these 20 ohm 10 watt resistors in series, and we measure the resistance from here to here, Well, the resistances will add up. They will add up numerically. We got 20 ohm, 20 ohm. Well, 20 ohms plus 20 ohms is going to be 40 ohms. So the resistors add up in series just like you'd add up any simple value. And being these are equal resistors and they're going to be dissipating equal amounts of heat, the wattage rating of this total package will add up the same too. You got 10 watt plus 10 watt. We have this is a 20 watt rating for the entire 2 resistor network. Now when we add when we wire resistors in parallel, they add up a little differently, and these examples we're use here today are going to be equal values because it makes the math simple. As we move on into Ohm's law and power calculations, you'll learn how to do this when it's not equal values. But 20 ohm here. This 20 ohm plus 20 ohm. Now because they're equal and we have 2 of them parallel, it becomes 1/2. So it becomes 10 ohms. We put equal value, 2 equal value resistors in parallel, as you see here, rather than the series as we just had before, the resistance will be halved of the total package. But again, because they're equal value resistance, the currents will split equally between them, and the power dissipated of each will split equally between them. So the wattage rate still adds up to 10 plus 10 for 20 watts for this little network here. Because we split the power equally, we can add the wattage rating up directly. Now we're going to go back to that original circuit that we had. Which these were 20 ohm, 10 watt. And we put them in series. It gave us a total of 40 ohm, 20 watt. Now if we take another branch just like this and add in parallel, again more 20 ohm, 10 watt resistors. So now we put what amounts to a 40 ohm in parallel with a 40 ohm. But they're equal values. 40 ohms represents this whole thing, by the way. And the same thing here. So it's like 2 40 ohm resistors in series. So from here to here, they split again. So we have 20 ohms. Again, equal values, all the power dissipation gets split up the same. So we can add up the 10 watts to give a total of 40 watt power dissipation. So what have we done here? We've got 20 ohms, which is the original value of our single resistor, but we've got 40 watts power dissipation, which is 4 times the power dissipation of our original 10 watt dissipation resistor. So by adding them up this way, we didn't change the total value, and we added them up, then we split them back. So the network here has the same resistance that one resistor originally had, but it has 4 times the power dissipation. So this is one way you could get a larger power capacity resistor if you didn't have one available, by combining the resistors you have. Now we're going to talk a little bit about what goes wrong, what can go wrong with resistors. Well, if you have a variable resistor for, say, a volume control or tone control, and you have scratchiness when you operate it, and you hear scratchy sound in the speaker, or if you're adjusting the bias on some circuit and you see that the voltmeter jumping around, your potentiometer is probably getting worn out. Occasionally you can clean it with some cleaning compound, spray in electroclean type stuff, but for the most part it's likely to be failing, wearing out. Resistors can burn open. They can also change value. If you want to check a resistor, let's say we have a little circuit. I'm just gonna call this 10 volts, and we go through a switch, and we'll call this R1, which is going to be 10 k ohms, and R2, which will also be 10 k ohms. Now if we put an ohm meter across like that, switch is open, we are not going to be able to measure the value of this particular resistor, which, if they're equal resistor, equal values, it wouldn't be too hard to recognize that it should be 5 k ohm. But let's just say that this was a 100 k ohm. Well, we're obviously going to get something less than 10 k ohms because that's the minimum. I haven't done the calculation, but we'll say we read 9 k ohms. Doesn't really tell us much about that resistor. So basically, if you want to read the value of a resistor, it's pretty much best to take it out of the circuit. Now when we disconnect one end, now we're going to see the full resistance of this R2, which should be 100 k ohms. But if we saw 50 k ohms, we'd know it was bad. Where 50k in parallel with 10k or 100k in parallel might not be that much difference. But so you want to take a resistor, at least one end out of the circuit before you read something. And if you're reading resistors with your ohm meter, say they're just in your hand, you do not want to put your fingers on the leads of the ohm meter, not because you're going to get shocked, because the ohm meter puts out a very low voltage for this testing, but if this was, say, a 1 meg ohm, 1,000 ohm resistor that you're reading, and you touch here and here, well, your body might have a resistance of 50 k or so. So you're going to get a really bad value. So you want to use some kind of a clip you can clip onto a resistor so that you're not touching the leads and putting error into your reading when you do that. Anyway, I think that will conclude our lecture for today on resistors. When we come back next time, we're going to get started on Ohm's law, which will help you calculate some of this stuff that we've talked about, and looking forward to it. And remember to subscribe so you get notifications on new lectures and such come out. And until next time, keep on learning.